Hello and welcome! Today, we're exploring the fascinating world of wave superposition and how it leads to the formation of standing waves.
So what is standing wave?
Waves with equal amplitude, wavelength, and frequency traveling in opposite direction is the same medium.
If your science class feels like a roller coaster, you're in for a treat. Let's talk standing waves. Standing waves are like magic in physics. Imagine plucking a guitar string. Those waves bounce back and forth, creating spots that don't move. These are standing waves. Fun fact, they're used in musical instruments and even in microwave ovens to heat your food. Cool, right? So next time you hear a perfect pitch, thank those standing waves. They might not move, but they sure know how to rock.
This is the equation of standing waves.
We begin with the two traveling waves. D1 representing a wave moving to the right and the D2 representing moving to the left. Notice their equation. D1 is equal to A sin Kx minus Wt. D2 is equal to A sin Kw plus Wt. A represents the amplitude, K the wave, X the position, and the W the angular frequency, and the T is time.
This slide shows the application of the standing wave equation.
So as you can see that the amplitude of a standing wave is dependent on its position. The amplitude AX is expressed as 2A sin Kx, which can also be written as 2A sin 2 pi over its wavelength. So we can simplify the standing wave equation to dxp is equal to ax cos times the wt. With the displacement dxt is equal to 0, there is zero amplitude and therefore exists a node. Conversely, when dxt is equal to 2a, this denotes maximum amplitude and therefore exists on antinode.
We will give you a short video that explains where they located.
So in the first part, we're asked to find out where the nodes are. And the nodes occur where we've got zero amplitude. So with our standing wave, which looks a bit like this, we need these points where the amplitude is 0. And the equation for our standing wave is 2a sine kx cos omega t. So this cos omega t just varies between 1 and minus 1. So what we need is the points where this part is equal to 0. The amplitude for the incoming waves can't be 0, otherwise we wouldn't have a wave. So what we actually need is that sine kx is equal to 0. And so this will occur when kx is equal to 0, or it can be equal to 180 degrees or pi radians, then 360 degrees or 2 pi radians, 3 pi radians, 4 pi radians, etc. And k, that's got the same meaning it always has in this topic, it's the wave number, so it's 2 pi over lambda. Okay, so we've got kx is equal to 2 pi over lambda x, and it's equal to 0, pi, 2 pi, 3 pi, just integer multiples of pi. And what we're trying to do is work out x in terms of lambda. So we can multiply both sides by lambda on 2 pi, and we end up with x is equal to 0, and then we've got pi times lambda over 2 pi, and then we've got 2 pi times lambda over 2 pi, and then we've got 3 pi times lambda over 2 pi, 4 pi times lambda over 2 pi. So now we can simplify this down a bit. So we've got 0, these pi's cancel out, so we end up with lambda over 2. Then these cancel out, so we end up with lambda. These pi's cancel out, and we have 3 over 2 lambda. And these cancel out, leaving a factor of 2, so we've got 2 lambda. So this tells us that these nodes occur every half wavelength. So one loop from here to here is lambda over 2. So if we actually want to measure the wavelength for a standing wave, we need to measure 2 loops, and that will give us the wavelength for one wave. Okay, B, we're then asked to find antinodes. So these antinodes occur halfway between the nodes. So they occur on these red crosses here where we've got the maximum amplitude. So the fast way to do it is to realize that the antinodes are halfway between the nodes, and then we can just divide our answer for x here by 2. So halfway between 0 and lambda on 2 is lambda on 4. Halfway between lambda on 2 and lambda is 3 lambda on 4. So that's one way to do it. The longer way to do it is to realize that the antinodes, these will occur when this term is maximum, and that'll be when sine kx is equal to plus or minus 1. So that occurs when kx is equal to 90 degrees, which is pi on 2, and then 270 degrees, which is 3 pi on 2. 5 pi on 2, 7 pi on 2, etc. And then again, k is equal to 2 pi on lambda, so we've got 2 pi on lambda x is equal to pi on 2, 3 pi on 2, 5 pi on 2, 7 pi on 2. Okay, let's cancel the pi's out now, and then we can rearrange this to get the x. So x is equal to lambda divided by 4 is what we get from this one. Here we're dividing by lambda on 2, so we end up with 3 lambda on 4. Here we end up with 5 lambda on 4, 7 lambda on 4, etc. So again, the distance between two antinodes is lambda on 2. And so if we want to measure one wavelength, we need to take 2 of these loops.
This slide shows the standing waves on strings.
A standing waves on string, when a string is attached to fixed ends, waves will reflect on the fixed ends and travel in opposite direction, standing wave. If the one end is denoted as the origin and the other end is denoted xl, is the amplitude of the origin, and the at of x equals L is 0. This equation tells us the wavelength E possible for standing wavelength string of length L. So M is just a number 1, 2, 3, 4. That determines which harmonic or mode of vibrant you're looking at, so different wavelength fit on the string. This slide is all about fundamental frequency of the wave.
Frequency is related to a velocity and wavelength. It is how many waves per second depends on wave speed and wavelength. When the longest wave 2L and the lowest frequency are achieved, it is defined as the fundamental frequency or the first harmonic. So this is the equation of the fundamental frequency. This shows the harmonics on a vibrating string.
Fundamental. This is the standing waves that we refer as the normal modes of vibrant of a string. Top wave is the fundamental frequency. The lowest note, the waves below are the harmonics. This is the harmonics. Higher frequency are often multiples as a fundamental frequency. Fm equals to mf1 equals to m equals to 1, 2, 3, 4. These frequencies are known as the harmonic resistant frequency. So, fundamental harmonic and the second harmonic, this is the third harmonic and this is the fourth harmonic.
Hello everybody. In this video we are going to be looking at the solutions to the Physics 1 Standing Wave Practice Problems 1. Let's take a look at our first problem. A pipe is 2.46 meters long. If the speed of air is 345 meters per second, A, determine the frequencies of the first 3 harmonics if the pipe is open at both ends, and B, what are the 3 lowest possible frequencies if the pipe is closed at one end? So we know that the length of our pipe is 2.46 meters, and the speed of the sound wave is 345 meters per second. In the first part, we are looking for our first 3 harmonics for the pipe being open at both ends. And if the pipe is open at both ends, I know I have both odd and even numbered harmonics. So I'm going to let me try this again. I'm going to want to find the frequencies for the first, second, and third harmonics. See, that wasn't very difficult to say. Gosh, I need a break. All right, but not yet. So for my first or fundamental harmonic, I know the frequency is going to equal the number of the harmonic times the velocity divided by 2 times the length of the pipe. So for the fundamental harmonic, I know n is going to equal 1, and I plug in my values for the speed of the sound wave and the length of the pipe. And when I do that, I am going to get a fundamental frequency of 70.1 hertz. For my second harmonic, again, the value for n is 2 because this is my second harmonic. Plug that into the formula along with my my speed of the sound wave and the length of the pipe, and I'm going to get a frequency for the second harmonic of 140.2 hertz. And for the third harmonic, I do the same thing. I just use the value of 3 for my value for n, and when I do that out, I am going to have a frequency for the third harmonic of 210.4 hertz. And just one last thing I want to point out in this problem, note that my second harmonic is twice the fundamental harmonic, and my third harmonic is 3 times my fundamental harmonic. Part B asks us to do the same thing as Part A, but only for a pipe that is closed on one end. And for a pipe that is closed on one end, we only have our odd numbered harmonics, no even numbered harmonics. So my 3 lowest possible frequencies are going to be my first, third, and fifth harmonics. So now I need to use my standing wave formula for a closed pipe. And I know for my first or fundamental harmonic, the value of n is going to be 1. I plug in my value for the speed of the sound wave, which hasn't changed from the first part. It's still 345 meters per second. And the length of the pipe hasn't changed either. It's still 2.46 meters. And I do that math out, I am going to have a frequency for the fundamental harmonic, frequency for the fundamental harmonic of 35.1 hertz. For my third harmonic, again, I'm just going to use the value of n is now 3 for my third harmonic. And when I plug that into the equation, I am going to get a value of 105.2 hertz. And for my fifth harmonic, I know I am going to have to plug in a 5 for my value for n for the fifth harmonic. And I do that math out, and I'm going to have 175.3 hertz for my fifth harmonic. And once again, note that my third harmonic is 3 times my fundamental harmonic, and my fifth harmonic is 5 times my fundamental harmonic.